The third day of the workshop. There's only talks this morning, so I'm sure our speakers will have your maximum concentration. And the first is Thomas Halsey, who's from ExxonMobil, and we'll be talking about frictional granular flows.
Thank you, Jim. Good morning. Okay, let's try again. Good morning. Okay, it's a very simple principle, which is you have the responsibility to be awake right now. It is my responsibility that you still be awake 45 minutes from now. So I'm going to I have to say I was a little struck when by the talk by Dr. Rogada on the first day, because he really led with his industrial side and emphasized aspects of granular flow problems that are of important economic value to his industry. And I hope I won't disappoint you by saying that I'm actually going to be taking somewhat of a different tack and going native in what is a somewhat academically focused conference, and actually giving a more academically focused talk about grain motions. However, I am available for anybody who is interested to tell you why ExxonMobil is interested in this subject at all, and it is in fact a subject of considerable economic interest to us. Okay. So the work I'm going to be talking about is the result of a long-standing collaboration with a lot of people. There are a couple of people on this list I really have to point out especially. The first is Denise Ertash, who is in another ExxonMobil laboratory than the one in which I work, who has been kind of my principal theoretical collaborator in this field for a number of years. And then the other person I particularly have to point out is Fuping Zhou, who has done most of the actual numerical work that I will be showing in the first slides of this presentation. Comment about the numerical work: it is a mix of things that I participated in and things that I actually didn't participate in. So if you start to probe details of the numerics, you may be lucky and find that I'm actually familiar with them, or you may be unlucky and find that at one or two questions down I start to flounder and wave my hands. Okay, so the overall aim of dense granular flow studies, I think, are familiar to all of us, which is to try to both develop a phenomenology, meaning in practice effective and robust constitutive equations to describe the flows, but also to advance our fundamental understanding of the micromechanics associated with granular flows, here represented as granular glows, which so there are always mistakes on the slides that you first see when they're up in front of everybody. And as a number of speakers have pointed out, this dense granular flow regime is intermediate between two regimes that are perhaps somewhat better understood. Certainly the collisional flow kinetic theory regime, I think, could claim to be quite well understood based on efforts of a number of people, some of whom are in this room. And then the soil mechanics quasi-static flow regime, in which everything becomes rate independent, and I think there are still a number of fundamental questions there, but it's also probably better understood than the dense granular flow. So the overall numerical approach that we took in the Exxon Sandia collaboration was a standard DEM type approach, such as has been described in detail by a number of speakers in this meeting so far, with an aim of simulating relatively large volumes to get some representation of the continuum and some idea of continuum behavior of these materials, and also start to unpick the relationships between grain scale motion and the constitutive relations. So the other important piece of background, which has been mentioned a lot in questions, but I'm not sure anybody has talked about it so much in talks yet, is this proposal by GDR Midi, an association of French researchers, which was that in the dense granular flow regime, the fundamental dimensionless group that is controlling the behavior of the system is the inertial number I, which is basically defined as the local shear rate times the particle size times the square root of the density divided by the pressure. Okay. And so GDR Midi have, in a series of very interesting papers, advanced their reasons for believing that this is the dimensionless group that will successfully collapse all of the different types of granular flows, provided one stays within the dense regime. Okay. Now, the physical interpretation of this, of course, I think is still a little unclear, at least to me, probably to others as well. In the theories of incline flow, we proposed, and in a somewhat different way, Jenkins has proposed, that there is a link between this inertial number and a length scale with a physical meaning that is somehow characteristic of the flow. And so it's easy to build such a length scale just by taking the particle size and dividing it by the inertial number, which you'll see from this formula up here actually eliminates the particle size and creates a pure sort of macroscopic variable corresponding to this supposed more mesoscopic to macroscopic scale L. Unfortunately, attempts to observe this scale directly by looking at, for instance, velocity correlation functions in dense flows have not been especially successful. There was an early indication that it might be there in some experiments, but unfortunately, when that was looked at more carefully, it turned out that that length scale was not quite the same that was being seen in experiments, was not quite the same as this. Ole Baran and us, we basically hit velocity correlations in every way we could to try to find this length scale, and we did not succeed. So our belief is that this is not this length scale, if it exists, is not reflected in an obvious way by velocity correlation functions. Okay. So I'm now going to tell you a little bit about what we have succeeded in seeing in the numerical work. And I'd say largely this is a confirmation of the proposal of GDR Midi that this parameter I really does allow you to simplify your understanding of the flows. So these three graphs are showing a combination of results that are obtained from a chute flow or incline flow, free boundary flow, and also from simple shear flow, simple shear in a cell. So what's nice about this is you see that you're able to really collapse data from two quite different flow geometries on top of one another. In terms of a dilatation law, what you see is that there appears to be a clear kink or discontinuity in the behavior of the density of the flows as a function of I, with that discontinuity appearing around a value of I of 1/4. If you look at the traction law, the ratio of the transverse to the normal stress driving the shear in the flow, this also seems to collapse quite effectively as a function of this parameter I. Again, for both the chute flow and for the simple shear flows, with a transition from a mu that is varying with I at low values of I to something that's much flatter with I at larger values of I. And then most dramatically, if you look at the velocity fluctuations, basically the square of the velocity fluctuation normalized by a characteristic velocity, which is the local shear rate times the particle size, you see that there's an actual reversal in the behavior of this around the critical value of I, where at low values of I, this is basically diverging as I goes to 0, and in the thermal regime, it's increasing with I, which in a way is the more what you would a more intuitive result. I should say that this this also has roots in G.D. Armidi, who observed that there was this divergence of the fluctuations at small values of I. What's really new here is the observation that there appears to be a clear distinction between a low I regime for this type of behavior and the larger I regime, which appears to follow more what we would expect from kinetic theory. So I think there are really a couple of messages from this slide. One is that, I think the G.D. Armidi proposal about I really does seem to be corroborated by our studies. And the second part of this is really that, the more you look at these things, the more you are able to convince yourself that the dense granular flow regime is indeed a regime. It is not a simple extension of the more kinetically described gaseous regime that you see at larger values of I, but it appears to have some fundamentally new physics going on that is perhaps going to be difficult to see by extensions from this kind of regime over here. Okay. Now, of course, there are a lot of parameters in these systems, in particular stiffness of the particles and the coefficient of friction of the particles. If you look at the stiffness, we are basically not able to see any significant effect of the stiffness. So the stiffness is these three pictures across the top with 10 to the 5th, basically 10 to the 6th and 10 to the 7th as effective dimensionless Young's moduli. And maybe in the kinetic gas regime you see a little bit of difference according to the value of the stiffness, but remarkably little given the 2 orders of magnitude difference that we're seeing here. And at smaller values of I, we're really not able to convince ourselves that we're seeing much. If you look at the coefficient of friction, what you see is that provided mu is greater than about 0.1, it's a similar story. The behavior of the system seems to collapse pretty quickly onto a curve that's characteristic of moderate values of mu. And at that point, it doesn't really seem to depend on mu any further. However, clearly, as you go to the frictionless regime, you're starting to see significant differences in the behavior of the system. Okay. So the lesson here is that stiffness seems to be not that important. And friction appears, provided it's big enough, not to be that important either. Okay. So this motivated us to try to think about a somewhat simpler version of this system, where we say, well, we are, and I could have incidentally shown you similar pictures in terms of the coefficient of inelasticity, where you would have seen similar weak results, provided there was some inelasticity in the system at all. So we are decided to consider systems with that were inelastic as they could be reasonably made, and also with very high, perhaps infinite coefficient of friction. So in such a system, once particles collide, they're going to have a rather hard time uncolliding. Okay? And the contact between such particles will typically be rolling contacts. So if you like, this is to motivate thinking about states in which all the contacts between the particles are rolling contacts. And what's nice about a rolling contact is that it creates a whole class of kinematical constraints on the system. If you look at 2 neighboring particles, ij, separated by the vector delta w sub ij, if you look at the difference in the velocity of those particles, basically the requirement that the contact be rolling. This is, incidentally, this is written in a form that's most appropriate for 2 dimensions, but the extension to other dimensions is obvious and can be obtained just by putting vector signs on things. So you have a relationship that the difference in the velocity is related to the sum of the angular velocities of the 2 particles. And the difference in the accelerations of the 2 particles is related to the angular velocities, and then the angular accelerations of the two particles. So basically, you pick up a certain number of constraint equations at each contact once you make this assumption of a perfectly rolling state. And in fact, if you look at the velocity sector alone, the velocity constraints alone, you actually pick up d, in dimension d, constraint equations per contact. Okay? So, for instance, and that's easy to see, for instance, in 2 dimensions, that you are constraining the normal velocities of the two particles, and then you're constraining the angular accelerations and the tangential velocities with one equation in 2 dimensions. In 3 dimensions, there's one normal constraint and 2 tangential constraints, and so forth. So you're always creating d constraint equations at a contact. And now that means that if you're looking at the kinematical degrees of freedom of the system, the total number of true kinematical degrees of freedom in one of these perfectly rolling states will scale with the total number of particles times, in 3 dimensions, 4 minus z sub c, once you do all of the arithmetic around the number of degrees of freedom. Right? So people who have followed the jamming literature and the static granular systems will recognize this as basically a result that is referred to as the isostaticity threshold. Has been used a great deal by Sir Sam Edwards in this university, by his collaborators, and by a number of others. And this is just exactly the same kind of counting, but now applied to a kinetic system and not to a jam system. Okay? So the critical number of coordination number in 3 dimensions is 4. So this says that if you have a coordination number of more than 4, you cannot make one of these rolling states. If you have a coordination number of less than 4, you can make an awful lot of them, scaling with n. And if you have a coordination number of exactly 4, you can, if you like, control the number of true degrees of freedom in the system. And in 3 dimensions, the corresponding critical coordination number is 3. Just the other comment I want to make about these rolling equations is I also wrote down the equation for the accelerations, which of course you could use to determine the forces. And simply by the dimensionality of the equations, you get the result that the Bagnhold scaling, that the stress tensor will go as the shear rate squared, occurs automatically in one of these rolling states. Okay. Now, just to complete the picture, I have to tell you, now we have this motion. Can these rolling motions last forever? And the answer is no. If you consider a graph of particles connected by these rolling contacts, as it moves, eventually the graph has to change, and contacts have to be destroyed or created. The creation of contacts occurs because particles will actually collide with one another due to their motions in this graph. And the destruction of contacts will occur because the normal force across a contact goes through 0. And then at that moment, the contact will fail, and you have a new network of contacts and a new set of constraint equations on the kinematics of the system. Okay? So that's all very nice, but rather speculative. Okay? I have shown that you can count up degrees of freedom and construct this sort of castle in the air about the possibility of this state, but that doesn't mean that anything like this state actually could exist in a real granular packing with interesting kinematics that were not completely pathological. So what I'm going to do next is I'm going to actually build you in 2 dimensions pictures of these states and tell you what they look like. And I do that by taking a very simple model system, which is a honeycomb lattice. So a honeycomb lattice is a Bravais lattice with a basis, and it has the virtue, from my point of view, that every particle in a honeycomb lattice has exactly 3 neighbors. So this is precisely the kind of case that should be interesting from the point of view of my rolling state. In 3 dimensions, incidentally, the equivalent is a diamond lattice, also a Bravais lattice with a basis, in which every particle has 4 contacts. I haven't yet had you will see that this gets algebraically a little bit complicated. I haven't yet had the appetite to do this in 3 dimensions. However, I have no reason not to believe that it's going to look qualitatively the same in 3 dimensions. Okay, so now I told you that I was actually going to do some work, solve all of these constraint equations for you, and show you what the results look like. So now I'm going to have to rely not on pictures, but if you will excuse me at this rather uncivilized hour of the morning, on equations. The way I solve this problem is I look at these 2 particles as a sort of fundamental doublet. Each particle has a velocity and an angular velocity, and I create 4 variables characterizing this doublet. The average x velocity, the average y velocity, the sum and the difference of the angular velocities of the 2 particles. Okay? And now, in order to solve the problem, I basically look at the constraints created between this doublet and its 4 neighboring doublets. And in fact, the structure of the problem is hyperbolic, okay? By which I mean that if I know the entire solution on this line, I can compute the entire solution on the next line and so forth. You can step this forward. So if you have, if you like, initial data down here, you can move forward and solve for the kinematics of the entire lattice. Okay? And so the form of the equation is that these 4 basic kinematical variables on this doublet can be determined from their values on this doublet, and on this doublet, j plus 1, k minus 1, if you'll excuse the indices, j minus 1, k minus 1, with 2 linear operators that are tedious but straightforward to compute. And you'll notice that I can do this for, I make these operators functions of theta, which allows me to basically write down the solution for any particular value of theta. So it's not just the symmetric honeycomb lattice, but any other, which will come back to be significant later. Okay, one more thing. So as you would expect, there are 4 solutions to this equation. The solutions have the block flow K form. They are, there is a Briand zone, a one-dimensional Briand zone, and everything for these solutions. And of these 4 solutions, 3 are acoustic, meaning they are motions kind of go to 0 in the long wavelength limit, and 1 is optical, meaning it involves rearrangements within a cell. So the acoustic modes, now I'm going to tell you, I'm not going to tell you about the optical mode because I'll run out of time, but I am going to tell you how to construct at home in the quiet of your own chambers all of the acoustic modes for this problem. Okay. So first of all, you pick one of these 3 directions in the lattice, and this is the state that corresponds to this direction. And then along one of the chains in that direction, you set the particles counter-rotating. So since this particle is rotating in the opposite sense to this particle, this point actually remains fixed. Okay? So if I look simply at this whole chain, none of these particles will move with respect to one another. If I go to the next chain and I do exactly the same thing, but I make the magnitude of the velocity slightly greater. Okay? So here it was omega, here it's omega plus epsilon, on the next chain it's omega plus 2 epsilon, and so forth. So now at each of these contacts, basically this chain picks up a net velocity with respect to the chain to its left, with the result that the whole state looks like a simple shear. Okay? And I can build as complex a motion as I like, any motion corresponding to these kinds of shears by simply superimposing the acoustic modes in these three directions. Okay. Right. Now, I haven't solved the problem yet because I haven't told you that these correspond to forces in which all of the normal forces have the right sign, are compressional and not tensile. If in order to build that state, I have to put in tensile forces, it's an interesting state, but it has nothing to do with granular media. Okay. So now I go back and to my fundamental doublet, and I put in normal and tangential forces at the four corners of that doublet. And I use geographical indications for that: northwest, northeast, southeast, and southwest. Again, the structure of the problem is hyperbolic. If I know all of the forces down here and I know all the motions, I can integrate up through the lattice in order to determine everything. I have now a homogeneous part of the force equation that does not depend on the local motions. And then I also have an inhomogeneous term dependent on the variation with time of these various kinetic parameters, and also the parameter gamma, which is just a dimensionless moment of inertia for the problem. Okay, so now the one other thing that I have to do is now I want to integrate these dynamical equations forward in time. So I'd better be able to keep in a honeycomb lattice. And that's where this theta parameter turns out to be handy, because by varying theta, I can create an extensional flow where I come in this direction along the x-axis and go out in these directions along the y-axis. So I actually have a one-parameter family of solutions that corresponds physically to extensional flow, which is a great convenience. I could do this for more complex flows, but then I would neglect my other duties. I would be so busy that I would neglect my other duties in ExxonMobil, and I would lose my job. Okay? So the fascinating things about that is that something bad happens, which is that if you look at the inhomogeneous part of the solution, now for the forces in this extensional flow, negative normal forces do develop. And in this kind of extensional flow regime, they develop in particular angular sectors corresponding to the direction of net expansion of the lattice. Okay. Not all is lost, however, because that's the inhomogeneous part of the solution, and there is also a homogeneous part of the solution. So if I increase the pressure in the system, which I do simply by adding to the homogeneous part of the solution, I can create larger and larger regions around the origin here, which are essentially don't have any tensile forces. So by doing so, I create these zones. So now I have these zones of suction with negative normal forces that I'm pushing further and further away from the origin. And if I say, as I increase this pressure, what is the scale of this region in which I avoid the negative normal forces? The scale of that region basically goes as d over gamma dot square root p over rho. This scale that I kind of thought existed before, but I was puzzling over the exact physical meaning of. Here the physical meaning is clear. The motions of the system are creating centrifugal forces, and at a certain point those will overwhelm the pressure and start to massively fail contacts. And the length scale that you have to be on for that to happen is determined by the pressure. Alternatively, you could say that provided you are dealing with patches smaller than this assumption of perfectly rolling states is an assumption that is consistent with the dynamics. All right, so that's a honeycomb lattice. Probably not very much seen by numerical studies of granular systems. So what happens if we go to a random lattice? Well, one of the interesting things about the honeycomb lattice solution is that it has a very natural structure, which is that what you basically did was you took the honeycomb lattice and you broke it up into two alternating sublattices, and you said that locally the angular velocity on sublattice A was approximately the opposite of the angular velocity on sublattice B, and then by varying with the differences here, the small differences, you were able to create all of the motions you needed to create in the lattice. So how are we going to do that in general? Well, the problem is we can't do it in general because once you create a general random lattice, you are going to create plaquettes which have odd numbers of particles around the plaquette. And so when you perform this decomposition into two alternating sublattices, sometimes you're going to have them in contact with one another. So in order for this to work, this kind of state still to work, you need to allow slip at these contacts because the relative angular velocity at these contacts is much, much larger because it's omega A, basically 2 omega A than any of the relative angular velocities any place else in the lattice. Okay? It turns out that there is actually a literature about this kind of problem in a different context, which is people interested in antiferromagnets on random graphs, where exactly the same problem arises of how do you effectively partition a random graph into two alternating sublattices while having as few as possible of these frustrated bonds. And that's a system that is believed to be equivalent to an Ising spin glass, to have spin glass ground states in 2 dimensions than to have an actual spin glass phase in higher dimensionalities. For our purpose, it's just reassuring to know that there are consistent ways of specifying these alternating sublattices that at least minimize the number of frustrated contacts. The final thing I have to say is there is an anticipation of this way of thinking about the states in a paper by Alonso Marroquin et al., who observed in 2 dimensions that there seemed to be 3 types of contacts. Contacts they called ball-bearing contacts, where particles were counter-rotating, slipping contacts, such as these, and then what they called regions of bulk rotation, where the particles were just locked together and were moving together, which would tend to collapse all of this interesting kinetics into a shear band of some kind. Okay. I don't have a lot of time to go through the rest of this in detail, so I'll try to stay at a pretty high level because I just wanted to really get to one more, I think, interesting comment about these systems. Now the question I'm faced with now is how do I compute more interesting things on these random graphs, like the relationship between 2 particle correlation functions and the overall motion of the graph. And there's a way of doing that, which is a so-called Fokker-Planck approximation. And the basic idea here is that we take a random walk on the lattice with the rule that we never cross any of these frustrated contacts. So at every stage, we're moving from a sublattice particle A to a sublattice particle B or back. So we're only staying to these nice counter-rotating contacts. And as we perform this random and the other assumption is that, it was not an assumption, it must be kind of true. There's a distribution function on each of these contacts, which is of theta, basically what's the angular distribution function of contacts in the system, and then what is the sum of omega A and omega B across that particular contact. Okay? So the great thing about Fokker-Planck is you build everything out of this distribution function. Okay? So in particular, at each step in the random walk, W changes and V changes, and the probability that W will go to a particular value of delta W, or that V will go to a particular value of delta V, can of course be traced back to this individual distribution function. Okay. So the rest of this is standard physical kinetics. You now say, over this whole random walk, what are the likely changes in delta W and delta V? So you use the central limit theorem to build that up, and that is an exponential of a matrix expression where the coefficients of the matrix can be connected back to cumulants of delta W and delta V at individual steps. Okay? So the equations look big, but the concept here is basically very simple. So, as an example, we can think about simple shear, where Vy is proportional to x and Vx is equal to 0. So in this case, we can actually compute that the Vy dx, which is the global shear coefficient of the system, can be related back to a simple cumulant of delta x, delta V sub y, divided by delta x squared, which basically allows you to start to understand how to build single particle distribution functions of theta and omega A plus omega B that will correspond to large scale shear. So that part of it is straightforward. Here comes the surprise. You can now go to the next stage and compute not an average of V, but an average of V squared. And so that you relate again back to various integrals over this master distribution function. And what you discover is it actually diverges for all dimensionalities less than 4. And the diverges with n, the total number of steps in the random walk. Now, we know that we're looking at systems that are supposed to be confined to a scale L. So if we say that our random walk, number of steps in a random walk, n squared goes as L, which would be a true random walk, then we can actually compute a divergence of the velocity fluctuations, which comes to L to the 1 minus d over 4, or in 3 dimensions, 1/4. Okay. So the good news is we've recovered this divergence of the velocity fluctuations with the inverse value of I, which was such a striking qualitative feature of the granular flows. The bad news is, boy, did we do a crappy job of computing the exponent, because the exponent that you see in the numerics is about 0.6, maybe between 0.5 and 0.6, and we're off by a factor of about 2 on that because we got an exponent of more of a quarter. So clearly the Fokker-Planck approximation, although we might feel qualitatively it's doing rather well, quantitatively we're having some troubles with it. Curiously, you get almost the right answer if you say that the result of all these frustrated bonds is to force the random walk to be much more linear than a true random walk. Then you would have get a result of 0.5, which is might actually it's pretty close to what we see. It's probably a little larger than 0.5, but that's close. Okay. Okay. So conclusions. Well, first, which I think this is becoming less controversial, and probably I think a lot of people have arrived at this from in different ways. But the numerics are clearly showing the dense flow regime is different, is qualitatively different, does involve some different physics from the granular gas regime. This honeycomb lattice is a relatively rare case of a problem that you can solve exactly in granular mechanics, which actually seems to yield some interesting results. So we get a qualitative understanding on the limit on the scale of the regions that can be subject to these frictional forces, which is consistent with previous dimensional arguments. We see that, in fact, these frictional states are characterized by having expectation values of W squared, omega squared, that are basically different from omega, average of omega squared. In terms of the random lattice motion, we had to add these sliding contacts to get a consistent picture. An interesting implication here is that if you actually take the coefficient of friction to infinity so that you can't have these sliding contacts anymore, the picture breaks down. So it suggests that there is something sick about the true coefficient of friction goes to infinity limit here. We got qualitative agreement on the growth of the velocity fluctuations, but certainly disagreement on the value of the exponent. And finally, there's nothing I've said here that's particularly limited to 2 dimensions. I think it's pretty easy to do all this in 3 dimensions as well. Thank you very much.
Yes, Mark.
So if I calculated right, your honeycomb lattice has a density of about 0.3.
That sounds about right.
Isn't that really low for the dense regime? So that if you were in the dense regime, you'd have to have many more contacts, and you'd be in the case where these rolling solutions were not really feasible?
Well, I mean, what I would say is that I can go with these random graphs, and I can create states that.
Well, if they have many more contacts than the 3, so that you'd be in the different.
Well, I mean, if the rolling state in 2 dimensions, I mean, Edwards is still right. If you've got a coordination number of greater than 3,
Yeah.
you're not flowing.
Right.
Period. So so I think the claim that
You're not flowing without sliding.
No, you're not flowing. Period. And we do know from the numerics that the coordination numbers are below the Edwards threshold in any state, be it dense or non-dense. So saying that the honeycomb is too sparse, that's a legitimate criticism. Saying it has the wrong number of contacts is not.
One more question?
With this picture in mind, so can you tell us now how to measure correctly in the simulation this characteristics length? Do you have an idea on that?
Well, I mean, what I would say is it is a region. To measure in the simulation,
Yeah.
I don't know. I know things I can tell, or in the experiment, I don't know. In simulation, I would look at spin glass order parameters, basically.
Have you tried now?
But we haven't tried that yet.
Okay, let's thank the